Hello guys, and welcome to IV Tutor. We are continuing with our linked lists, and in the previous video we looked at nodes, and we basically wanted to understand the foundation of linked lists, which is using nodes. Like, how do you use nodes to build up a list? Pretty much like the syntax, moving pointers, linking nodes together. I emphasized on those two lines of code in the previous video. So if you haven't checked that out, please make sure you do, because it's really necessary for you to understand everything else we're going to be doing in this video. So today we want to look at the linked list type, and everything we are doing when we want to look at the linked list type class. That's what I meant to say. And everything we are doing, remember, it's based on the recommended textbook. So this is where the whole idea, the whole logic, the whole approach that we are taking comes from. So if you have been looking at linked lists, you realize that we have this class referred to or called the linked list type class, which is a template. The textbook takes a whole approach, to before it gets here, but eventually this is what you really want to worry about. And the main fundamental principles I want you to understand on this class is the fact that it has these three member variables and a private. Okay, this means private. So there's a count variable, which is used to maintain or to keep track of how many nodes you've got in a list. We've got first, which is a pointer, and we've got last, which is a pointer. And first is a pointer which is used to always point at the first node, and last is a pointer which is used to always point at the last node. So whenever you build a list, these three variables here are the ones being used to maintain a list. And these public functions that you see are there to manipulate the list, which means your linked list type class is representing a list, and it has exposed all these functions which allow you to search a list, to get the item at the front of the list, to get the item at the back of the list, to get the length of the list, to display the whole list, to insert the item as the first item in the list, to insert the item as the last item in the list, to delete a node. So all these functions are simply working on this list. So what's actually happening is that we've got all these nodes that are linked together, and what's happening here is that first is always pointing at the first node, and last is always pointing at the last node, and count is always keeping track of how many nodes you have in this list. Whatever operation you do on this list, this is always its state, which means if we insert a node as the first node, it means first then moves to that first node. If we insert a new node at the end of the list, it means last then moves or points to that last node. So the list is always looking like that, which means all these functions are simply manipulating this list. And whatever you do, it should always remain like this. First referring to the first node, and last referring to the last node. And then count keeps track of how many nodes you have. And your job in this case is to have the ability to implement any of these functions or any function which does not yet exist. Now, I want to get one thing off the way very quickly. The linked list type class is the base class, right? So if we draw this, we've got the linked list type class, which is our base class. Inheriting from this class, we've got an ordered linked list, an ordered linked list, and we also have ordered linked list. Ordered linked list. What this means is that the questions that you answer may use any one of these three classes. They can use the linked list type class, they can use the unordered linked list class, or they can use the ordered linked list class, just depending on the question, right? But you realize that in most cases, we are going to be, when we actually get to using or running the code, you only instantiate these two classes. This one is referred to as an abstract class, or actually it's an abstract class, which means you cannot instantiate it, but that's a conversation for a different module, not this one. What only matters in this case is that these are the three classes you're going to be dealing with, and for the most part in exams, you are here or here. Very less likely, are you here? I've seen this in some assignments, but I haven't seen this a lot in exams. Most of the exam questions that you get are mostly based on the linked list type class or the unordered linked list. So what this means is that all these functions that are defined here, some of them do have an implementation at this level. Some of them do not have an implementation at this level, because in another linked list is simply a normal list where ordering is very important. But an ordered linked list is more like a sorted list, which means your nodes will maintain an order based on the sorting order that it maintains. By default, it's ascending order. So you realize that a function like insert last would behave differently in such a class like this one, because if your last node is not the largest value, it cannot be the last node, right? And so forth and so forth. Or your search function. It's different when you're searching a sorted list. You might want to use the binary search algorithm, but if you are searching an unordered list, you might want to use a sequential search algorithm, which means the implementation of these functions can then differ here and so forth. But basically, this is the bigger picture in terms of the classes that you are going to be dealing with. But most questions, they just say, do this function which belongs to this class if it's just a general function, or sometimes it can belong to this class. And very, few instances, it can be part of this class. And your job is to have the ability to manipulate this list, which is being handled, in other words, by these three variables. First is always pointing at the first node, last is always pointing at the last node, and count is the number of nodes that you have. And whatever you do, that should not change. Let's look at a few examples of the type of questions that you get under the linked list type class, so that you can start understanding how you do the code and the syntax and everything. But remember what I said before in our previous video, the most two important lines of code: moving pointers, linking nodes. That you must never forget, because for most of these questions, once you get that syntax off the way, are based on logic. You have to be able to create a pseudocode or understand the steps that you're going to take to solve a problem, because once you do that, the code follows the logic or the pseudocode, right? Let's look at this question, for example. It says provide a member function, right? Member function means it's part of the class. Like it says, of class linked list type. That determines the maximum element in a list. Use the following header. There you go. Which means this function is actually going to be in part of these functions. So they are saying, well, let's add one more function to these functions. And this one is called max. And what this function does is it returns the maximum element in a list. In other words, it returns the largest element inside a list. All right. So you do know that your list has first pointing at the first node, followed by a whole bunch of other nodes. And then you've got your last pointing at the last node. And then you've got your count, which is keeping track of how many nodes you have. This is all you have. That's all you're going to work with, right? And you have to check this list for the maximum or the largest element of this list. All right. So how do you find the largest item in any collection, even in an array? What is the algorithm like? What is the logic? How do you do it? So basically, before we come back to this question, let's just understand that part, because if we start writing code and you don't know what we're doing, then it means you just won't understand the code that we are writing. So let's start off by addressing, how do you find the largest element in a collection, like in an array, right? Let's have an example. It's a very simple algorithm. I think you should have used this a lot in other modules. So let's say you've got an array here with some items, and you've got numbers here, like you've got 2 here, you've got 3, you've got 1, you've got 9, you've got 6, 5, 8, and 7, for instance, right? And you want to find the largest item in this collection. The first step is to assume that the first item is the largest. So you create a variable called max or largest, whatever you want to call it, and you assign it with the first item, which is 2. Then you start checking from the second node or from the second item going forward. And what you are doing is for each item that you visit, you say, is this item greater than the maximum so far? If yes, you change maximum to 3. You keep going. Is this one greater than 3? No. Is this one greater than 3? Yes, you change this to 9. Is this one greater? No. Is this one greater? No, no, no. And then you're done. And then you return your value of maximum. That is also the same logic that you use when you're trying to find the smallest item in a collection. It's a very simple algorithm. Assuming that the first item is the smallest or largest, start looping from the second item going forward, And for each item that you visit, compare the current value with your current largest or smallest. And then if the current item is greater than the current largest, then update the current largest. And you keep going like that. That's the algorithm. So it's very easy. Now we want to do this, but on a list. What's not going to change is the algorithm. We want to assume that the first node has the largest value, and then we start looping from the second node going forward. And I'm going to do this. I'm going to write the steps first, and then we'll do the code, right? So let me just draw a line here so that we can, just discuss exactly what we want to do, and then we can do the code, and then you can see the correlation between the logic or the pseudocode sort of and the code that we are then going to write afterwards. So we said that step number one, assume that first node is max, right? So for this line to work, it means we have to declare a node, or we have to declare a variable called max, or right? So in other words, we declare max and assign it value of first node, right? Of first node. That's all we are doing here, right? And then the second step is we then want to loop from the second node going forward, okay? So we want to loop from second node upwards or forward, right? From the second node going forward. And as we do that, we are going to check if the current node is greater than maximum. What do? You update maximum. And then you keep looping. When you're done, you return your largest value or your maximum. Three simple steps. So let's write the code, and let's talk about one of the most important things you must never forget when looping a list, okay? So our function here looks like this: template plus type, and then we've got type here, type linked list type of type. It's called max, like that. So what is step number one? Step number one is, let's assume that the first node is the largest. So we can declare a variable called max, which is of type if we want, or just m. And we can assign it with the value of the first node. So you can say m equals to first dot info, like that. Now, secondly, we want to loop from the second node going forward. But here's the danger. Never lose the address of the first node. Do not forget this rule. You must never lose the address of the first node, or in other words, you must never lose the head of your list. Why? Because look, if you have nodes that are, in a list like this, and so on, right? And your first is here. If you move first from this node to this node, how else are you ever going to get back to that node? There's no way. Because the only pointer that knew the address of the first node was f. Now you've modified f with the address of the second node by moving it forward, which means you can never go back to the first node ever again. If you keep on moving f as you traverse the list until you get to the last node, what this means is you have just lost this list, because you have no way of going back to this first node, because the only pointer that knew the address of the first node is f, which you have changed. So whatever you do, you must always make sure that there's a pointer, pointing to the first node, which means first must never be moved. First must always be pointing at the first node. That allows us to have the ability to loop through this list over and over and over again, because we still have the address of the first node. That is why we've got this pointer first. Last is there for convenience, okay? It's there for convenience. If you want to put a node at the end of the list, it's very easy because there's already a pointer at the last node. So that's why we always make sure that last is always pointing at the last node. Now let's come back to this story. So how do you then loop through a list? What you do is you introduce another pointer, right? Current is very, very, very popular. So you introduce another pointer, let's say called current, and you can move current from here to here, from here to here, and you can keep moving current until it gets to the end of the list. But your first remains at the first node. So current is simply a pointer that you introduce for the purposes of looping through the list or for the purposes of traversing the list, which means you can move current from the first node to the last node without any worries because you know that first is always going to be pointing at the first node. So what you do is for you to traverse a list, you introduce another pointer that you can use to traverse. So in this case, I'll introduce a pointer called current. So I'll go node type of type. Let's call this one current equals first dot link. Why first dot link? Because we want to start from the second node. Remember the algorithm. We said you assume the first node has the largest value, then you start checking from the second node going forward. If we wanted to loop from the first node, we would simply assign current to the first node, or move current to the first node, or point current to the first node. But because we want to start off from the second node, we go current equals first dot link, right? Which is now step number 2. Now, how do you loop? Usually it's a while loop. So you simply go while, which means as long as your current has not yet reached the end of your loop, then keep moving, okay? So you're going to keep on moving current, pointer equals current dot link. Again, you remember from the previous video, pointer equals means you are moving current. We did a lot of examples in our previous video. We talked about, moving P and Q, trying to find what the code was doing. So, P equals P dot link, and we said we are advancing P twice. Current equals current dot link means we are advancing current once forward, which means we are simply moving current to the next node, which means eventually your current becomes a null value. So as you do this, what you want to do, we said as we loop, we want to check if the current value is greater than our maximum value. If it's greater, then we update the value of our maximum. So we can simply have a simple if statement that says if our current dot info, if the value of the current node is greater than m, which is the current value of the largest element, what do? We simply want to update m to current dot info, and then we keep moving. That's all we are doing, which means by the time this loop is done, m is actually, or m has the value of the largest node. So here we go current dot info. Now remember, we don't know what type really is because this is a template. So we don't know if we can use the greater than sign to compare items in this list. And that is the reason why they say you can assume that the list is not empty and that the greater than operator has been overloaded for type, which means don't worry about, what if these are, other types of variables that we cannot compare with the greater than sign. They are saying, don't worry. You can assume that the greater than sign is going to work for whatever type this is, which means we can safely just compare the two values. And that's your code. After that, what do? We return our m, and our function is done. So you realize that the most important thing in these questions is to understand the logic or the pseudocode, understand exactly the code you are trying to write, or understand the problem you're trying to solve, know exactly the steps you're going to take in solving that problem. And once you know that, all you do is moving pointers and linking nodes. In this case, we are simply moving pointers. We haven't really linked any nodes. So we introduce our maximum variable. We introduce a new pointer called current, which we use for looping or for traversing the list. And then inside our loop, we compare the current node's value to our maximum value. And if the current node's value is greater than the current maximum, we simply update our maximum to the current value of our node. We keep doing that. We keep traversing current until current becomes null, which means until current gets to the end of the list. And then we return m, and we are done. Right, so it needs a lot of practice to get used to the code, to get used to crafting the solutions and, understanding how you want to solve the problem. Now let's look at this other question, which is a bit different, and we'll see why. This one says implement the operation occurrence counter, which is part of the class linked list type. Okay, this operation counts and returns the number of occurrences of an element in a list. Use the following header. So you've been given the function, and they say, here is your linked list type class. It looks like this. You need to count how many times an item occurs in a list. Like how many times is a value appearing in a list, and then you return that count. So it sounds simple, right? Because all you want to do is get the value, get the list. So one thing to take note of in this question is that this function is being given the list as an argument, which means this is the list that you are using. It's unlike this question where this function is in the current class, yes, and we are simply using first here to refer to this guy. In this question that we are doing, we are being given another list as an argument. And our job is to then count the occurrence of this value in this list. But this list is an instance of linked list type, which means it has its own first, it has its own count, it has its own last, right? So that is all you are doing. So instead of us just going first, last, no, we are referring to first and last of this list. But what is the solution? We simply want to loop through the list. As we loop through the list, we have an if statement that says, is the current value equal to, okay. If it is, what do? We increment our count. And then eventually we return our count. That's all we want to do, which means let's quickly do this. Where am I? Here. Okay, perfect. So let's write the code. I think we can, I'm just going to write some comments and then we can start writing the code. So it's a template function. So we are going template class type. It returns an integer. It's called occurrence counter. It takes a linked list type, and it's called list. I think it's by reference or something. It's called list, and then it takes a value called OK, like that. That's our function, right? Let's just confirm that. All right, that's it. Okay, so we are saying that we simply want to declare an integer value, right? So the first thing we're going to do is define an int variable to keep track of our count, right? What do you want to do next? You want to loop, and in the loop, check if current node is equal to OK. Then if equal, what do you want to do? Increment our counter. That's all you want to do. So the logic is quite simple, right? Define a count variable, loop the list. As you loop, count. So let's start by defining an int variable here. So let's go int counter equals 0, right? Now let's go loop. We said whenever you loop a list, never lose the address of the first node. So we need to introduce another pointer that we can use for looping, right? I'm going to go current, and we're going to say current should begin at list.first. Now remember, I'm referring to the first, which is inside this list. It's very important. If this function was just like this, which means it's a member function, we want to count how many times this OK in the current list, we'll just go, well, let's start from first. But remember, in this case, we are counting from this list that we've been given as an argument, which means we are referring to the first inside this list. That's where we start. Then we start looping. So we can then say while, current is not equal to a null value, what do? We want to check if the current node, so we can go if current.info is equal to OK, then we can counter plus plus. We can increment our counter, and then eventually we return our counter. So that is the basic, algorithm that you would want to use or the basic code for this sort of question. But one of the most common things that happens with these questions is you have to check for exceptions, fringe cases, things like, what if it's empty, right? So in that case, you can then here do something like, if list.count is equal to 0. If the list is empty, then just return 0. Don't waste time. So you can do things like this. This is not really exception handling because the code would still work even if you don't do this, right? But this could be just for efficiency, like, well, we don't need to go and execute all these other lines of code if it's empty. But that's also something that other people prefer doing. Things like, so in this case, there isn't really much there aren't really exceptions we need to handle. Things like, what if it's not there? It will still work. What if the list is empty? It will still work, right? So you can leave your code just looking like this. That's actually fine. I hope you guys can see my font size here. Just to be safe, I'm going to just increase it a little bit just so that everybody can see. All right, that's the code for this question. It was very straightforward. Get the logic right. Once you get the logic right, once you know exactly what you're trying to do, then it's easy to then write the code. Let's look at another example. Okay, this one is very interesting. It's a very interesting question that I've seen a couple of times. It's also a very popular question in a lot of exams because it's quite tricky to understand, but it's not really a difficult question to do. So let's slowly understand what's happening in this question. Let's understand the solution, then we can write the code, okay? Because it looks a bit scary just looking at the hint. You are very lost if the hint you're given is not even making sense. It means you are far off where you're expected to be, But if the hint makes sense, that means you're in the right direction. Okay, because I've seen students who complained that the hint made things even more difficult. So actually, you are very lost. So if we look here, it says, consider the definition of the class linked list type given in Appendix A. It's the same class. Provide a member function of class linked list type that determines the minimum element in a list. Use the following header. Okay, remove min. Hint, declare the following variables. All of this, okay? So this function needs to find the smallest item in this list, like we did before. So this part is actually very simple because we've just talked about how you would do that. Assume the first item is the smallest, and then, keep looping. You have your if statement, and then, you do that. But in this question, we are not trying to return the value of the minimum element. We are trying to delete it. So we have to find the smallest item and then delete that item. So what steps are you then going to take in solving this problem? And where am I? I'm trying to find my space here. These questions, I want to go here. Okay, thanks. All right, so let's think for a minute. So if you have our list here with, let's say, let's go to which links to 8, which links to 4, which links to 1, which links to 6, which links to 7, and then 9 eventually. Let's say your list looks like this, right? Your job is to go and find this node and then delete it, okay? Now, the problem with deleting a node is that the continuity has to be there. We cannot just delete a node and then now we've got this space or we've broken the list. It should still remain a valid list, which means after deleting 1, 4 should then continue connected or linking to 6, okay? So deleting a node requires 2 variables. So if we zoom in on this part here, we are saying that we have 4 connected to 1, connected to 6, and this continues and this continues. Now, if we find out that 1 is the smallest node, and then we put a variable here, let's say we put a pointer D on 1, on this node 1, right? What we want to do is to simply go delete D. This will go and delete this node, but then there's a problem because it means now from 4, we are linking to nothing, and then we lose all these nodes. So you cannot just delete. What you want to do is you need to link 4 to 6 and then delete this node. Now, for you to achieve this link, we need a pointer sitting here so that we can then link 4 to 6, right? So this brings us back to our 2 lines of code, moving pointers and linking nodes. So if we put a pointer on 4, let's say we put a pointer called P here, that means we can then successfully delete D by going first, let's go P.link equals, we want to link P to what? To this node here, which we can refer to as D.link or as P.link. So I can just go D.link. Executing this line will result in this node 4 linking to 6, which means this line is gone because we've changed this link. And then step number 2, we can then go and delete D, which means this goes and terminates this node. Remember, a node is made up of a value and a link, so this is then deleted. And now we have a valid list. 4 continues to 6. The main thing I want you to see is that if you want to delete a node, there has to be a pointer sitting on the preceding node. If you want to delete this node here, 1, we need a pointer sitting here so that we can perform this link. If we don't have a pointer sitting here, it means we cannot delete this node. Or we can just do it, but it breaks your list. So deleting a node requires 2 pointers. One that's sitting on the pointer you want to delete, on the node you want to delete, and another pointer that is sitting on the preceding node. And the purpose of this pointer is to then allow you to link this preceding node to the node that comes after the node you want to delete. So deleting a node is a 2-person job, a 2-pointer job, okay? It requires 2 pointers to achieve. So now that we understand this part, deleting a node requires 2 pointers, the one sitting on the node we want to delete and another pointer sitting on the preceding node, which allows us to link the preceding node to the node after the one we want to delete. If we go back to the question now, we want to find the smallest node in the list. Once we find it, what do we want to do? We want to delete it. So according to your algorithm, what you are going to do is find the smallest node, which means when you are done, you're going to have a pointer sitting on the node that you think is the smallest. So if we remove this, we are saying that your 8 here, your node is linking to this node 6, which links to this node 1, which links to this node 7, for instance. Okay. So in this case, let's say we want to use this pointer smallest to point to the smallest node, which means we do our algorithm, we look through the list, we compare nodes, and once we are done, smallest should then be sitting on the smallest node. And eventually, we want to do delete smallest. But we know that this is going to be difficult to achieve if we did not also keep track of the node that is behind smallest, or in front of smallest, if you take this as the front of the list, right? So if you don't take note of this node here, which is in front of smallest in the sense that this is the first node, or which is preceding smallest in the sense that the arrows are pointing this way, whichever way you understand it. It means we won't be able to delete smallest. So the algorithm that we need to use to find the smallest node should also make sure that once we find the smallest node, we have a pointer sitting on the preceding node. Okay? And our algorithm is going to be very simple because it's going to work like this. We are going to say, let's start by assuming that smallest is the first node, exactly the same way we did before, right? Which is also first, by the way. First is also this same node, right? Then we start looping from the second node going forward. If the value in the current node is less than the value in smallest, we make this node smallest. Otherwise, we ignore. So we go here. Is 8 less than 2? No, we go to the next one. Is 6 less than 2? No, we go to the next one. Is 1 less than 2? Yes. Therefore, we update smallest and we make smallest this node, which means we change our smallest from this node and smallest comes here. And then we keep looping. Is this one less than smallest? No. Is this one less than smallest? No. Which means by the time we are done looping, smallest is now sitting on the smallest node. But there's a problem. We have no pointer behind smallest. Therefore, there's no way for us to then delete this smallest node. So we need to do this with 2 pointers. Let's rewind, okay? If we rewind, we are saying that we start by assuming that the first node is the smallest, right? And then we start checking from the second node going forward. Now we're going to need 2 pointers. We're going to need smallest, and let's call the other one prev smallest, meaning previous smallest or preceding smallest. And the job of this pointer is to point at the node behind smallest, which means in our loop, if we say, if the current node, if current dot info is less than smallest dot info, that's our loop, that's our if statement. If the current node is less than our smallest, we said we want to update smallest. So we are saying smallest, we move smallest to the current node. So in other words, we are going smallest equals current. The difference between this question and the one we looked at before is, in this case, we are not keeping track of the smallest value. We are keeping track of the smallest node. You get that? Because here, we were interested in the largest number. So we kept track of just the value. If we were keeping track of the largest node, we were going to assume that first is the largest node, which means this would have been a node, like node type of type. So here we were keeping track of the largest value, not the largest node. A good exercise for you is to do this same question, but for the largest node, not value. The only change is this becomes a node. And here, you don't say m equals current.info, you say m equals current, because you want to move your node, your pointer, to the current node and say this node is the largest, which is what we are doing here. We are keeping track of the smallest node, which means if the current node, if the value of the current node is less than the value of our smallest node so far, we move smallest to the current node, pointer equals. And we are also saying that if we use 2 pointers, we are saying we must move smallest to the current node, and we must move prev smallest to the node behind current. Okay? Which means when our current gets here, we want to move smallest to here and prev smallest to here. And then our current will keep looping until it gets to the end. And when we are done, it means our smallest is here, our previous smallest is here. Now we can delete this node because we've got a pointer here and a pointer here. Which means when you loop through your list, you need to use 2 pointers as well. So eventually, your logic will look like this. You're then going to say, assume that the first node is your smallest. I'm just going to use S just to make it easier to write, okay? I don't want to write smallest every single time. So I'm going to use this S for smallest, PS for previous smallest, C for current, PC for previous current, okay? So remember, you assume that the first node is the smallest. And then you start looking from the second node, which is your current. And we are saying that when you start, assume that the first node is the smallest, put your previous current here, put your current here, put your previous smallest also on the first. It doesn't matter where you put this one, really. It doesn't really matter. I can just put it here if I want. So when I start, all these 4 pointers are pointing at this first node. Smallest is assuming that this is the smallest node. Previous current must always be behind current. So if we are starting from the second node, previous current must be behind current. Previous smallest doesn't really have to be here, but it doesn't matter because if we update smallest, it means that we also update previous current. So you're saying, let's start by comparing if 8 is less than your smallest. No. So if no, it means current moves to the next node and so does your previous current. So these two move together. So what you're going to do is say, okay, so current moves to the next node, which means your current goes to 6 and your previous current goes to 8. Then you say, is 6 less than smallest? No, right? Therefore, these two move to the next node, which means your current then moves to 1 and your previous current moves to 6. So your current goes here, your previous current goes here. Then you say, is 1 less than 2? Yes. Now you update your smallest to become current. So you say, okay, that's true. So this is now the smallest node. So current, smallest moves to current. And you move previous current, smallest to previous current, right? So your smallest and your previous smallest both follow suit. So you say smallest moves to current, previous smallest moves to previous current. Then your current and your previous current will continue looping because you're not done yet. So your current will go to the next node and so does previous current, which means your current then goes here, your previous current goes here. Then you say, is 7 less than 2? No. So these two again continue moving, right? So your current moves to 9 and your previous current moves to 7. Let's say, just for the sake of explanation, this was 0. Guess what? It means we were going to say, is 0 less than 1? Because now your smallest is here. And then you were going to say yes, which means your smallest moves to 9, your previous smallest moves to 7. So these two move together. So in other words, what makes this question special is that you loop with 2 pointers so that when you find the smallest node or whenever you update smallest, you also update previous smallest. Now in this case, 9 is not less than smallest, therefore your current moves and it becomes a null value, your previous current becomes 9, and once your current is equal to a null, your loop terminates. And guess what? Your previous smallest is here, smallest is here. Now you can delete smallest, which means now what you need to do is to go previous smallest dot link equals smallest dot link, which means you link this node to this node, right? And then once you have done that, you can then delete smallest. Oh, let me just go yes, delete smallest like that, which means this node is then deleted. So that is the idea behind this question, where you use 2 pointers to loop and 2 pointers to delete. The reason why you use 2 pointers to loop is because if you then say current is less than smallest, you want to be able to move smallest to current and previous smallest to previous current, so that when you then want to delete, you have a pointer sitting behind the node that you want to delete. So if you go back to the question now, you see what it says here. Sometimes they use the words previous current or trail current. Like in this case, they are using current, previous current, smallest, trail smallest, which is the same thing as previous smallest. Or they can say current and trail current, smallest and trail smallest, or smallest and previous smallest. It doesn't matter. But at least they have given you these 4 nodes because you use these 2 for looping and these 2 for deleting. And you can see the setup. We start by assuming that the first node is the smallest, which means our current starts from the second node. Previous current starts on first because previous current is always behind current, right? So if current is on first.link, it means prev current is on first. Like we did here, current is here, then prev current is here. Then prev smallest, smallest is the first node because we start by assuming that the smallest node is the first one. So smallest starts on first. Trail smallest is first. This one doesn't really matter where you put it. You can ignore it totally, or you can just, because when you update smallest, you're going to update it as well. But it starts off on the first node. It doesn't really matter where it starts. Okay. So your code is going to do exactly what we described. You're going to keep on moving these 2 pointers until you find the smallest node. Once you find the smallest node, then you delete. So let's now write the code. Okay. So let's go. Okay, template class. So we go template class type. This one is a void function. It's called remove min. So it's linked list type of type. Function is remove min. And there we go. Now, there we start. We are introducing new pointer, node type, current equal first dot link as it is, node type. Then this one is prev current equals first. Then we've got node type of type. This one is smallest equals first. We have node type of type. This one is, they say this trail smallest. Trail smallest equals first. Right, now let's loop. Okay, so let's go while current is not equal to now, which means as long as current has not yet reached the end, what we want to do, same algorithm. We want to check if current dot info is less than smallest dot info. Is the current value less than the smallest node so far? If yes, which is true, right? Then what we want to do, we want to make current the smallest node, which means smallest equals current. We move smallest to current. And remember, we also move trail smallest to prev current, because current and prev current are moving together, right? And then what do? Our current moves, our previous current also moves, which means there are different ways of doing it. You can go current equals current dot link, which means advanced current. And you can also just go prev current equals prev current dot link, which means advanced also prev current, because they move together. Or someone might go, well, I want to start by advancing prev current to where current is, because current is always ahead, right? So someone might go, well, let's move prev current to current, and then let's advance current. It does the same thing, because remember, current is always in front of prev current. So if you move prev current to current, and then current advances forward, they just keep moving. So that's all we're going to do in this loop until the loop is done. So you can see we keep checking if the current node is less than our smallest. If it is, we move smallest to current, trail smallest to prev current, and then these two keep moving. Once we are done with this loop, it means smallest is now sitting on the smallest node. So we can then say, well, let's link trail smallest to the node after smallest, which means we can now go trail smallest dot link pointer dot link equals, remember, you're linking a node 2, then you can go smallest dot link, and then you can then delete smallest. Basically, that is the general logic, which is exactly what we've done. What we've done here. ps.link equals s.link, delete s. But now let's talk about a few exceptions that you need to handle in these cases. Number one, what if the list is empty? Right? So you can then say, well, if the list is empty, we don't even need to do anything. We don't even need to loop, because if we try to do this or do all of this, it's not going to work. But sometimes they say you can assume that the list is not empty. All of that here, they said you can assume the list is not empty and that the operators greater and less than have been overloaded for type O. So we don't have to worry about the list being empty in this case. So that we can forget about. But that's not all. What if the first node was the smallest? Do you realize that this logic will not work? If the first node turns out to be the smallest, will this work? Let's find out. Because remember, we said that our first is going to be on the first node, right? Which links to the second node, third node, and so forth. So if our smallest is here, trail smallest is here, and then we go trail smallest dot link equals smallest dot link. What is this line doing? This line is saying link trail smallest, which is this node, to smallest dot link, which is this node. So this line is linking this node to this node, which is the node that the link already exists. So it doesn't really change anything, because we are just linking this node to this node, which is what it's already linked to anyway. That's fine. That won't change anything. It's inefficient, but it works. And then we say delete smallest, right? Now we go and delete this node. Now here's the problem. This is where first is. So if we delete this node, it means the whole list is gone. So in other words, if the first node happens to be the smallest, all we really want to do is just move first to the next node and then delete this node. You see that? So I can then update my code here, and now I'm handling those exceptions and say, well, if it turns out that, if first is actually smallest, if this is the same pointer or the same node, then, well, let's move first to the next node. So first equals first dot link, and then we can delete our smallest. Okay? So I could say delete smallest there. I'll tell you why I won't do it now. Well, let's just do it. So I can refactor later. And then let's delete. All right, that's fine. What if the last node is actually the smallest? What do we do there? What if the last node is actually the smallest? Let's go and check. So we are saying if the last node is the smallest, which means here we've got our last sitting here. Now smallest is also here, and obviously our previous smallest is here. So if we say, trail smallest rather, trail smallest is here. So if we say trail smallest dot link, which is this guy, equals s dot link, it means we are linking trail smallest to this node, right? So we are actually going to link this node to our now value, because this is a now value. So that's fine. There's nothing wrong with that. So this works. And then if we go delete smallest, it means this node is now gone. But the problem is that last is here, which means before we delete that, if the last node happens to be if the last node happens to be smallest, you want to move last to trail smallest. And then we can delete last. Okay? So we can then say here, well, in that case, we can say, let's move this a little bit up so that we can keep everything in view. We can say last equals trail smallest, right? So we move last to trail smallest before we can delete smallest. This is fine because it will just link your trail smallest to the null value. So it's fine. Again, I can still do this if I want, okay? In here, it doesn't really matter. Otherwise, if the smallest node is not the first one and it's not the last one, then we can just go ahead and do what we wanted to do anyway, right? Which is this code here in the else. What we've done is we've said, what if it's the first one? Because we want to move first to the next node. Oh, what if it's the last one? Because we want to move, oh, then we delete here. Then we delete smallest. So what I wanted to say before is I don't have to say delete, delete, delete in all these cases because I'm going to delete anyway. So I can just put this line here at the end because eventually I'll do it, right? I'm going to do it anyway. So I can just say delete smallest right at the end after all the if else statements because I'm saying what only matters is that if the first node is the smallest, let's advance first. If the last node is the smallest, let's advance. Let's move last to trail smallest. Otherwise, let's link smallest.link to smallest. Trail smallest.link to smallest.link. And then now we can happily delete smallest. So these two statements here are there to handle those exceptions where just in case your smallest node is the first one or your smallest node is the last one. And then you can delete. And I've seen this question a lot of times in many different past exam papers using different variables and different pointers, but exactly the same question, which means you can actually practice this question and get comfortable with it, understand the idea behind looping with 2 pointers, the idea behind deleting nodes, because it's very crucial. It's very important that you are able to do this. Okay. The last thing we need to do in this question is to decrement our count. Our count should now go down by 1 node. So here you should always remember to do count minus minus. So this says we have deleted 1 node, therefore we must also reduce our count by 1. So don't forget to decrement your count in this type of question. Okay, right. This is also one of the most common questions I've seen on linked lists, and this one wants you to divide a list. And you can see that it uses the unordered linked list class. It doesn't really matter. It's a linked list, right? And it says implement the operation divided, which is part of the linked list type, right? The usual class. This operation divides a given list into 2 sublists. Consider the following statements. My list, sublist. Suppose my list points to the list with elements 34, 65, in this order. The statement my list.divide at sublist 3 divides my list into 2 sublists. My list contains these elements and sublist contains these elements. Use the following header. Okay, what's really going on here? Okay, what's really going on here? They are saying we have a list, this guy, that is made up of these nodes. Okay, so this list has 34, which points at 65, going to 27, 89, and then 12. Okay, and we have a function as part of this class called divided, such that if we call this function on this list, the one which is this guy, it actually divides the list at position 3. 1, 2, 3, then it divides. So it's going to divide such that it remains with the first 3 nodes, and it gives the other 2 nodes into the list that you gave it as an argument. So you see that the divided function takes 2 arguments: the list that is going to get the remaining half or the remaining elements, and the position at which it must divide. Which means the first 3 items are remaining in the current list. Then the other elements are going into the other list that we have been given as an argument. So you have a list here, my list. So this is happening in your main function, for instance. You make 2 variables of type lists, my list and sublist. You call this function on this one, which means the instance which is executing this function is remaining with the first 3 items, and the instance that you're being given as an argument is getting the remainder of these items. Okay? So how do we then divide this list? Let's look closely at what's really happening in this question here. We have 34, 65, 27. Let's just write this down. This is your first. This is your last. We've got these nodes 34, 65, 27, 89, and 12. First is at 34, last is at 12. And our count is obviously 1, 2, 3, 4, 5. So our count here is 5. Let's just write that down. Our count is 5. This is in my list. Now, inside my list, we are going to call a function divide it and give it another list, sublist, as an argument. But remember, sublist also has first. Sublist also has last. And sublist also has a count. Right? These are variables of all, these are all linked lists. So we want to make sure that once we have divided, these 3 here remain inside my list, and these 2 here end up in sublist. In other words, sublist should then look like 8, 9 as the first node, 12 as the last node. If there were more nodes, then we could keep on going, basically. And the count should then be 2. And in my list, this should then be our last node, and the count should then be 3. This is the status that we are trying to achieve. And what's interesting in this question is that even though it feels like, you should be doing some copying of some sort, you don't copy anything. You simply play around with your links, because these are all pointers. So what you want to do is to just make sure that first of sublist becomes this node, and last of sublist becomes this node. Last of my list should then move to this node, and then you break this link and you update your counts. You have divided. Because now first for sublist is here, last for sublist is here, your last for my list is now here. You have broken this link, so these just become 2 different lists. So if we draw it, we are saying this now just looks like this. Your last here is obviously gone. It's now sitting. It's now sitting here. So this is now your last. Your sublist first is now here. Your sublist last is now here. Your count here is 2. Your count here is 3. That's all you want to do. And this is obviously still the last node. So the process of dividing is not involving copying. You are simply playing around with the links. Okay? So what you have to be careful about, though, is the steps that you take in modifying these arguments. Like what do I do first? And what you really want to do in this case is you can start by, you need to get to this node first, which is where you want to divide. Okay? So the first thing is to figure out, where am I dividing? Figure out the position where you want to divide. because you are going to eventually need to move last to become that node. Okay, so you are going to need to put a pointer here, P, for instance. So the first part of the question is to make sure that you traverse the list and you get a pointer on the node where you want to divide, so that you can then move last to this node. We'll talk about that later. It's easy. How do we get a pointer to this node? In this case, we are simply counting to 3. So we can just introduce our pointer, move it 3 times, or move it 2 times, 1, 2, done. We are there, okay? And then we divide. But once you've got a pointer here, the sequence of steps that you want to take to divide is going to be, I would go number 1, let's make last of sublist this node, because we've got a pointer here called last. So I would move, or let's use red for sublist, that we can keep track of who is who here, right? So red is going to be sublist, right? So sublist. So I would move last of sublist to this node as my step number 1, right? As my step number 2, I would move this last here to this node, so that this becomes my last. Okay, let me just erase this part. So this becomes my last of my current list, which means it's no longer here. So this becomes my step number 2, so it's gone. My step number 3 would be to make first of sublist this node. That's step number 3. And my step number 4 would be to break this link here. That would be step number 4. And step number 5, update the counts, which means if I'm dividing at 3, right? If I'm dividing at 3, my count of list is going to be 3. So my count is my new count, right? The position is my new count. If the position is 4, then I've got 4 items remaining in my list. If I'm dividing at 5, then I've got 5 items remaining in my list. So I can simply say, well, so the count of my list is simply going to be my position, right? And the count of sublist is going to be the original count minus the position. So sublist's count would be the original count minus the position, which means if I had 5 nodes minus 3, I'm now left with 2 items. That's how I'm going to update my counts. So once again, I'm saying that your new count of nodes in your my list, linked list, is simply going to be your position. If you were dividing at 4, it means 4 nodes are now remaining in my list. So your count is position. And inside your sublist, I'm saying your count is simply the original count of my list minus the position. That's your new count. But if I can do these 4 steps, I have divided the list, right? I'm going to try and draw this again more clearly, right? So that we can all follow through what's going on here. So we've got 34 here, which links at 65 to 65, which links to 27, which links to 89, which links to 12, which links to nothing. This is my current first. This is my last. And I want to divide at this pointer P. Sublist is here, but sublist also has first. Sublist also has last. So I'm saying step number 1, point last to there. Step number 2, move last to P. Step number 3, point first there. Step number 4, break this link. Step number 5, update your counts. And you have divided the list, because your last is now here. Your first for sublist starts here. Your last for sublist ends here. There's no continuity here. Therefore, these are now 2 different lists. You see that? So if we go back to the code that we are trying to write, it then becomes simple, because all I want to do, let's just write the header function together here. So we are saying it's a template. So we are going template class type right? It's a void function, divide at, it gets a linked list type of type, and this one is called sublist, and we have an integer position, which can be any number, right? And we said the first thing we want to do is to have a pointer at the node that we want to delete. I'm going to use P, so let's go node type of type. Let's call it P, and I'm going to say equals first, because I want to be able to move it from the first node until I get to the third node. So what I'm going to do is I'm starting off with P sitting on the first node, and I'm going to count from 1. So I can go off, I can start counting from 2, whatever way you want to do it, whichever way you want to do it. So I can go 1, 2, 3. But if I'm looping, remember the first time I loop, I'm here. Second time, I'm here. So I can start counting from 1, 2, 3. So I can say start from 1, then 2, then 3. It depends on how you want to do it. So you can also work out the logic and start counting from 0. It all depends on how you want to do it. So what I can then do in this case is I can have a for loop, because I'm counting, isn't it? So I can simply say, well, since I'm counting, I can use a for loop. You can still use a while loop if you want. It doesn't change anything. So I can go for int I equals 1, I less than count. Remember, there's a variable called count inside this list, I plus plus. I'm going to keep moving. So as I loop, I'm going to keep moving P. P equals P dot link. But remember, I only want to move up to position. So if P is 3, if position is 3, I'm going to say, well, I is 1, I is less than 3, I plus plus, then we move P, I becomes 2, so P has moved once. We come back here again, no, this will be less or equal to 3, right? Because we want to end at 3. So in this case, I'm just saying I is going to start off at 1, which means here. Then we say, is it less than 3 years? Therefore, let's move it. I becomes 2. 2 is less or equal to 3 years. Then let's move it. I becomes 3. And then we stop, because after that, it becomes 4, and then the condition fails. But there are so many different ways of counting it. You could still start from 0 to position -1 if you want. It also works. So this is all I need in order to move P to the node where I need to divide, which means after this, P is here. So after P is here, now I can do my 4 steps, which I've explained here. Move last to here. This one moves there. First moves here. Then we break this link, which is now easier, because all I can do is I can say, move last of sublist to the current last. So I'm going sublist.last equals, that's the one I'm moving. Pointer equals means moving a pointer. Sublist.last equals last. So what have I done here? I'm saying, well, the last of sublist must move to our last, which is 12. Step number 1. Step number 2, let's move last to P, right? So you can go, well, last equals P. Last equals P. Step number 3, move sublist first to the node after P. So I can go sublist.first equals P dot link, the next node. Then step number 4, break the link. So I can now go P dot link equals now. Link P to nothing. Remember, linking nodes, moving pointers. That's all you're doing. P dot link means you're linking it to a blank, which means I am breaking that link here. This guy. P dot link equals now this is gone. Now the last thing I have to do is update my counts. So I can now go and say sublist dot count equals the original count minus pos, and my current count is equals my pos, and I have divided my list. The next thing you would want to do in this case is to handle exceptions. What if the list is empty? What if there's only one node? What if you're dividing on the last node? And I'll leave these for you guys to practice. Okay, if you have any questions, you can come through to our live classes and we can talk about this. But here they said there is more than one node. So we don't have to worry about those exceptions because they say you can assume there's more than one element and that POS is greater or equal to 1. But what if POS is greater than the number of items that we have? So one of the exceptions you can do here is to simply say, well, if POS is greater than count, if the position is greater than the number of items that we have, let's not do anything. You can just return. That's one exception you can handle there. The other exception is what if we are dividing, or that one is out because POS is greater than 1. The other exception is what if POS is the last node? What if it's the last one? Is it going to change anything? That's for you to go and practice and find out. Okay. So yeah, please, let's keep on practicing. I think these are all the examples and the linked lists that I wanted to cover with you guys, which are the most common confusing questions. You now just have to practice. There are different variations of these questions, okay? There are different variations of these questions. Like I can tell you in this case, you can have divide at, which means you're given an index. Another variation says divide mid, which means divide in the middle. So you have to calculate the middle on your own by going count over 2. The other one was, there's divide at, then there's divide mid, which means divide in the middle. So it's a slight variation to this one because here you have to calculate the position on your own, right? By using the number of nodes that you have. And the same goes for the rest of the questions that we've covered. There are slight variations to these questions that you can encounter in exams. For example, if we go back to this question here that we did, remove min, you can have remove max. Another interesting one here is divide at. There's also divide mid, which means divide in the middle. There's, which one is this one? Remove min. There's also remove max, which you can also see in exams. And so forth. I mean, there are countless variations of these questions, and I haven't even covered all types of questions that I've seen. But these ones that we've covered in this video are the most sort of common ones. And if you can work through these ones comfortably, I don't think there is going to be any linked list question you won't be able to do, even if it's not covered here, because you really get how the logic works, how do you come up with a solution, the pseudocode, and how do you implement that solution. This is where most people struggle, because if you just look at this code, it looks really ugly. It looks like, I don't know, some Greek or something. But if you take things slow, get to understand the syntax, which is why you need the previous video on nodes to understand moving pointers and linking nodes, because that is all we do in these cases, linking nodes and moving pointers. Pointer equals means you're moving it to, pointer.link equals means you're linking it to, and the rest is just logic. It takes a lot of practice to start getting comfortable with this code, and doing it. You have to do it over and over again. Sometimes I would recommend you to start by attempting these same questions and see if you can reproduce the code, not because you crammed it, but because you actually understand the logic, and you can reproduce the logic, and you can reproduce the code, because that shows that you actually understand linked lists. And again, this is the most difficult part of this course, which means it does require that extra effort and that extra push to get used to this syntax. So please, let's practice. Let's keep on practicing. I'll see you in our live classes. Please keep on practicing. If you have any questions, compile them. And when we meet in our live classes, we can address those questions. That is it for me. I'll see you again in the next video. Cheers.